This is a video from my lecture notes, specifically the examples in my note sections related to gravitation. We had just finished our lecture on gravitation, universal law of gravitation. And these are four examples of how to use that knowledge that we just gained. We have a figure that shows two identical asteroids. These asteroids are large out there in space, by the way. They're not just a little rock. They're located near each other, but they're not in contact with one another. We have various locations on them, and they are labeled A, B, C, and D. If an astronaut wants to stand on one of those asteroids and experience the largest net gravitational force, where should the astronaut stand? So we will just assume that there's only three things because, again, if I'm in class, I have the Earth acting on me, this gravitational force, and then I have a gravitational force from infinite number of items and people, but they are small compared to the Earth. But let's just focus on if maybe we only have these two astronauts and asteroids and this astronaut. I'm going to call this asteroid number 1, and this is asteroid number 2. And then I'm going to think about what would happen if I'm standing right here on A, or location B, or location C, that person standing right there, or location D. So I'm going to look at each one of those locations, and I'm going to draw a free body diagram of the person that's standing at A, and I'm going to only look at the force of gravity, gravitational force that is being experienced by that person. So if I was standing at A, the person would have a gravitational force from the asteroid number 1, and it would point towards the center of that asteroid. So this is point A, and I will call that, again, gravitational force is big G, mass 1, mass 2, and r squared. And so if I was located at A, there would be a force of gravity from asteroid 1, and it would be equal to big G times the mass of asteroid 1 times the mass of the astronaut. So I'll call that, instead of M2, I'll just say M naught. And then we also have so I'll call that like this. This is force of gravity from asteroid number 1 on that person. Then I also have a force of gravity being created on that astronaut from asteroid number 2. And notice the distance from A to the center of asteroid number 2 is larger than the distance from A to the center of asteroid number 1. So that force of gravity would be smaller because that R is larger, it's in the denominator, and it's squared. So I'll call that force of gravity on the astronaut from asteroid number 2. So that's why that vector is smaller, okay? Now, let's look at B. I know there's a force normal. I don't care about force normal. All I care about is the largest net force. Notice those force of gravities acting on that person when they're standing at A is located in the X, we'll call it to the right, and they were in the exact, we'll call it exactly to the right, and they would then add together because I could have to add them vectorially. Force of gravity is a force and it's a vector. Now, if I go to B, I'm going to stand at B. I'm going to put a dot as if I'm standing at B. And I'm going to have they're identical asteroids, by the way. So the masses are the same. Now I'm going to have a very large force, but it's not to the left directly, it's towards the center. This is force of gravity acting on the person that's standing at B from asteroid number 2. And then I have a force, oh, it's smaller. Why is it smaller? Because the distance away is much larger, and r in the denominator is squared. So I have a little one kind of moving that way. I'll call that FG1. Okay, and this is when I'm standing at B. And when I'm at C, now I'm going to put C over here, I have force of gravity from 1. And then I've got force of gravity. I don't know which one's bigger, but you'll see what doesn't. This is when I'm standing at C, and it's to the right because it's pointing towards the center of that planet. I'm sorry, that asteroid. And then D, kind of like B, except that I'm going to have one kind of pointing downward, and that'll be FG from asteroid number 1, and one kind of going kittywampus, and that's kind of smaller actually, wouldn't it be? And that would be from FG2, and this is as I'm at D. And they want to know the largest net force. These two are working against one another. These I have to add vectorially. These I have to add vectorially, and hope you see that A is the largest because they're both in the exact same direction, so they get to added directly to one another, and A is the correct answer. Okay. We've got a satellite moves in a circular orbit at a constant speed v0 around the Earth. Let's draw a picture. Here's Earth. Here's my satellite. It's a perfect circle, we assume, unless otherwise told. I'm at some distance r. This is r from the center of Earth. You see it says center. The force exerted on the satellite is F0. So if I were to draw a dot, the only force acting on it is F0, which is the force of gravity from Earth. Okay. Then I have an identical satellite that orbits at a distance 3r. So now I have another one that's going to have three times the radius. How does the tangential, I could go and draw that if I needed to. Now I'm 3r around this identical, which means the masses are the same. How does the tangential velocity of the new one, well, here's the velocity in the tangential direction, and here's the velocity they told us is v0. How does that compare? Look at all the answers. Its velocity of the new one which is equal to some factor times the velocity of the old one. We're going to I'm going to work on the Earth one first. I'm going to sum the forces inward. This is around Earth. First conditions is equal to the force of gravity. That's the only force acting on it, inward. Mass of the satellite times v, they called it v0 squared, and the radius was r, and there we go. Now, go ahead and plug in what the definition of force of gravity is. I'm not on the surface, so it's mass of the Earth, mass of the satellite, divided by the distance to the center of mass is squared, which they said was r, mass of the satellite, v0 squared over r. We're interested in understanding how v0 changes. So I'm just going to go ahead and get everything over to the left-hand side of the equation except v0. Mass of the satellites cancel. We divide both sides by ms. We're going to move one of this r over. We're going to multiply both sides by r, and then take the square root. So I get the square root of gravity mass of Earth over r equals v0. Now I'm going to do the same thing for this new condition, this second satellite, and I will sum the forces inward. That is equal to the force of gravity acting on the second condition. Okay, this is the second condition. And that is equal to mass of that satellite times, and they're calling that v sub t squared over, now it's 3r. I'm going to expand force of gravity, big G, mass of Earth, mass of the satellite, same masses, remember, and notice the distance away is 3 times, and we got to square it. Mass satellite, BT squared over 3R. Move everything around, solve for BT, and I get the square root of big G, mass of Earth, mass of satellites cancel. I get 3R over 3R squared. So one of the 3's canceled, and I should get 3R. And that is equal to velocity tangential of the second set. Now, I want VT equals some number times V naught. I can easily just take this. VT equals some number times V naught. And I just need to know what that number is. So I can divide VT by V naught. That's one way. And I can do that over here. I'll just do that over here. Well, actually, no, I'm going to save that space. VT is the square root of big G ME over 3R divided by the square root of big G ME over R. And that will equal, this cancels, R cancels, and I'm left with 1 over the square root of 3. And that's the factor. And so we know that VT is equal to the square root of 1 over 3 times V naught. That simplifies into 1 over the square root of 3 times V naught. Now there's an easier way, and I will do it over here, and it's called factor of change. Find the factor of change. Once you have an equation, there's a whole video and a handout on how to use the factor of change. Once you know the equation for the variable that we're interested in, which is the tangential velocity, and I just highlighted that in yellow, I'm going to look at each one of those variables. I'm going to rewrite that. V naught equals square root big G mass of Earth over R. There's the relationship between the velocity and the mass radius of the Earth and the planet's orbit. And I'm going to calculate this factor of change. Look at each one of those items. Ask yourself if it changes with the new set of conditions. No, on big G, it's a constant. The mass of the Earth doesn't change. The radius was increased by a factor of 3. So I'm going to put a 3 there. And we find the factor of change is equal to the square root of 1/3. Now, what do I do with that? The V new is equal to this factor of change times the V old. And V new was, they called it V sub t. Factor of change is square root of 1/3 times V old, they called it V naught. And you get the same answer and a heck of a lot less maths. There's a whole handout and an instruction video on how to use factor of change. Number 3, 2 kilogram object is a distance of 10 million meters away from the center of Earth. Here's the Earth, here's the object. Mass equals 2 kilograms. We are R equals 10 million meters. What is the approximate gravitational field strength of the Earth's gravitational field at that location? Well, what am I asking for? G equals question mark. Earth has gravitational field lines pointing directly towards it, and at this location, there is a strength of that gravitational field. The equation for that gravitational field is the big G, universal gravitational constant, times the mass of the planet or asteroid. In this case, it's the mass of the Earth that's causing that gravitational field, divided by the distance to that planet's or Earth or asteroid's center of mass squared. So in this case, it's 6.67 times 10 to the negative 11. That's off your green sheet. That's the value of the universal gravitational constant times the mass of the Earth, which is 6 times 10 to the 24th, and then divided by r squared, which is 10 million meters, and I got to square it. And if you plug that into your calculator correctly, don't forget that negative 11, use your second function, comma, I believe, which is double E, and I believe you'll get a 4. And what are the units? Little g is gravitational field strength, or acceleration due to gravity, meters per second squared. A lot of times they will write it as 4 newtons over kilograms. That is the same as meters per second squared. That is the value that we get. That is how much gravitational field is exposed to the 2 kilogram object that's located 10 million meters away. Notice we did not use the 2 kilogram mass. That was given to you as a way to confirm you understood how to calculate the gravitational field strength. It is big G times the mass of the planet, or the large item that's creating that gravitational field, divided by the distance away from the two objects. One's the planet, one's the little object or spacecraft, distance away from their two center of masses. Sometimes the radius, not always the radius. This last problem is the only problem I've seen in many years worth where you actually have to use the big G equation, or I'm sorry, the potential energy due to gravity equation when you're not on Earth. So we have a force of gravity equation equals mg, and we have a potential energy due to gravity, which is equal to mgh. And this applies when little g is constant and so I like to say on the surface of a planet, right? Or the Earth. When does this equation apply? Big G m1 m2 over r squared. Always. It applies always, but you have to use it when you're not on the surface. And then we also have to use potential energy due to gravity where little g is not constant, and that would be negative big G times m1 m2 divided by r. Don't square it. It's negative y because we are not in control of the zero line, and it's located at an infinite distance away, so we're always under it. And we now have 3 objects. I'll call this object 1, object 2, and object 3. Normally, if we had to determine the system, here's a system for you, block 1, and here's block 2, and here's the ground, and I wanted to know the potential energy due to gravity total of the 2-block system, and let's call that the zero line. I would have to find the potential energy due to gravity of 1 plus the potential energy due to gravity for number 2, and you would add them together. And those would be positive numbers because they're both above the potential or the zero line. So we're adding the potential energy due to gravities at that spot. So it's the same approach, except look at this equation. I have to have pairs. So the potential energy due to gravity total after they were moved from infinite apart from one another to the location there is equal to, well, how many pairs do I have? I've got the potential energy due to gravity from objects 1 and 2, plus the potential energy due to gravities from objects 1 and 3 as compared to each other, plus there's a pair, plus the potential energy due to gravity from objects, I'll call it 2 and 3. I wouldn't go 3 and 1 because I've already got that. I wouldn't go 2 and 1 because I've already got that. So I would then calculate what that is. It is the negative big G. So let's look at 1 and 2. So what is the mass I got to have mass 1, mass of 2 divided by, oh, they're just located at R away from one another. They're not, the R's aren't squared. I'm going to add now another negative number. This is between 1 and 3. 1's mass is m, 3's mass is 2m over r. Now I've got to add 2 and 3 together. Negative big G, object 2 is an m, object 3 is a 2m, and then we have r. So I have negative gm squared over r minus big G 2m squared over r minus big G 2m squared over r. They're all the same. Every one of them has a G, an m squared, and an r. A G, an m squared, and an r. A G, an m squared, and an r. So I can add them. They're all common terms. So I have negative 1, minus 2, and minus 2. That would be negative 5g m squared over r. Again, only one I've seen in 10 years where I actually had to calculate the potential energy of a system of objects out in the universe. There's your answer. That concludes this video.